Okay, Magenta session again, Deutsche Telekom. So my name is Hans-Jörg Kolbe. Some of you might have seen me doing shameless advertising for this talk this morning. Actually, the key guy in this work is Leo Nobach, who couldn't make it here, who's also working for Deutsche Telekom. Okay, let's dive into implementing a programmable service edge. And I will explain a bit what that means, what we have in mind, why this is important for us, and I will also point you to our currently available P4 implementation that you can download on the ONF site above. Okay, Access 4.0, I think on day 2 of this great conferences, I think everybody has seen what Access 4.0 is. Access 4.0 is the Access Network Virtualization Program in Deutsche Telekom. It's actually not a virtualization program. It's a program to redesign the access network driven by the factors cost efficiency and scaling and operation, or let's say designed for lean operations. This you have also seen if you have attended some of the talks. We are building a system that is sort of a mini data center that is located in our access network. In Germany, we are talking about roughly 900 sites. So Germany is not a big country and it's densely populated, so there will be, in every place in Germany nearby, there will be one of these PODs, point of delivery, where we put these mini data centers, and the idea is, or what we'll do is we'll collect different types of access technologies and provide access to the IP network, mainly internet access, but also VPN access or whatever's gonna come with regards to overlays or sliced network, whatever. But the focus of our program is to deliver high-speed internet access over FTTH or FTTB, in our case, GPON. The cost model is not there to convince our management. No, it's there because this was important for us in the beginning of this program to do a decent cost calculation to see whether this approach makes sense. Actually, what we did is we looked at Cord, I think roughly 2 years ago, installed it in our lab, got some feeling on what works, what doesn't work, and made ourselves familiar with the technology, and in parallel did a cost case around that. And the work I'm presenting here is basically a consequence of the cost case. This is where we are at the moment. I had to take out the animations because of some PowerPoint issues. What you see on the right-hand side is this is sort of looks a bit like RDD2 if you like Star Wars. It's of this height. It's a small portable setup of our mini data centers. This has basically everything that you need. It has a bare metal OLT. It has a bare metal top of the rack switch. It has a bare metal spine switch. And for this setup, maybe too many servers, but a bunch of servers that run the control plane. This is everything you need to collect fiber access and to create IP services there. Yeah, I think Robert has also explained this one. This is just to get you up to speed. Now, with regards to this architecture, these mini data centers, we all know Cord, we know SIBA. I don't need to preach to the choir, so we have SIBA and UPAN that are closely related to what I will explain in the future, further in this talk, because I will talk about the BNG. The animations are gone, so I will talk about this part, the BNG, that can be, in some cases, outside the SIBA POD, depends on how you, in which phase you roll it out, or whether it's embedded in the POD. Looking a bit at the SIBA architecture, basically, actually, this is not the latest SIBA architecture, but since I'm doing a public presentation, I thought about, let's not put the intermediate stuff here. In SIBA, we have a couple of key components that are also in our Access 4.0 pod. So they are listed on the right-hand side. And first of all, we have an SDN control plane there, and we can run applications on it. And we have implemented our own way in steering traffic to multiple service edges to control the traffic. And that is basically an SDN applications that we have developed in-house. We make massive use of open hardware, OLTs, switches, DPUs, automation, sure, network management, IT abstraction, the Las Vegas principle that Robert talked about, and the service edge. And this is what the rest of this talk is about. And I nearly fell off here. Interesting. OK, BNG. Who knows what a BNG is? Everybody, great, okay, skip. So here's the slide. Usually access networks look like that. You have an access device in the home, you have aggregation or you don't have aggregation depending on how your networks look like. And then you have the BNG, which does the service creation, which creates the first IP hop. And the BNG is actually the coolest box you can work on if you work in networking. Well, let's say this is my opinion because I spent like 15 years on that. It's also the thing where most of the things can go wrong. And if you're on duty and over the weekend something fails, it might be that it's the BNG because it's a very complex box. It terminates the subscriber sessions. In our case, it's PPP over Ethernet. This is unavoidable in Europe unless you live in Switzerland, I would say. They have IP over Ethernet. PPPoE is there, and we can lengthy discuss whether we want to do PPPoE or directly move to IP over Ethernet, but there are things like regulation, long-term contracts with wholesale customers. And once you've done through the exercise of looking into when can we get rid of PPP over Ethernet, it's a bit far out. I would love to do IP over Ethernet, but I can't neglect that PPP over Ethernet is here, and we plan to deliver something in medium time frame, 1-2 years from now. So let's not get rid of that if we can't get. So, okay, it applies to subscriber services, and it acts as a full PE router, so the whole IP routing stacks are in there. The history of that, this is a bit the history also of my professional life. You start with a BRAS. Back then you had ATM access. Now we have, then we had Metro Ethernet, and then the BNG term was coined by the Broadband Forum, and usually there's no access or aggregation network between the access node and the BNG. You directly plug them in, and the BNG has become a single service creation point, a single point of failure also. This is an important thing I want to address. And later on, starting 2011-12, people started to virtualize BNGs, put it on x86, and now we talk about splitting control and user plane and putting the user plane on something that might scale better than x86 does. But over the years, we had growing complexity and growing throughput. I don't want to complain too much about growing throughput because those are our customers. They are happy with our network and they pay my salary. So let's better find something that serves the needs of the customers instead of complaining too much. But we have to find efficient ways of producing the service. Does this have a laser pointer? I don't think so. Okay. So let's address 2 key points here. I don't want to stand in the way of the photo, so I should go here. No kidding. 2 things. The complexity issue. I mentioned already that the BNG is probably the coolest thing in the network, but it's a single service creation point. It's a single point of failure. So if you directly attach your OLTs to the BNG, you need to produce all services at this point. This is cool in the beginning because you have only one box where you engineer the services on, but the moment you start adding more and more services on it, it gets complex because, for instance, your line cards, they need to be able to support every service, all the QoS profiles, and sometimes you have dependencies between different types of customers. Some need 8 queues, some need only 3, but in many combinations, you end up having to apply the maximum amount of queues to all customers. At least this is one example from the past. Some cool ASIC designs don't require that anymore, but it just gives you a feeling on that you have all these requirements on one box. So what we said, okay, let's use SDN here. SDN, I give lectures at university every now and then. 3 things, it's centralized control, so path control, it's about common APIs, and it's about programming the silicon. And when I did the last lecture for university, I figured out in A4 we're actually doing all these 3 things. Here's the centralized control on the left-hand side. We steer the traffic through our switching fabric to dedicated service edges. And that is done by a pretty simple SDN application that we have coded on our own. And I think probably most of the people in this room can also do this, for instance, on top of Honors. So this was the first thing we did. We steer traffic to where it is best being served. Now the next thing, when we did this, we did the calculation and, okay, let's put different types of service edges in. Standalone boxes from our vendors that we can currently buy, virtualized systems, and did the math. And then we figured out that, let's look at what's happening here. We hit a programmable chipset in the OLT. We hit one in the leaf switch, another one in the leaf switch. Then we go to a server. Then we go back again to a programmable chipset. We cross a lot of programmable chipsets, and we don't really leverage what we have in there. So we thought about, OK, let's split the control plane from the user plane. Everybody's doing that. But if we can offload the user plane processing to the ASICs that we are anyway traversing, we can take a huge cost driver out of the model. And we have also optimized routing. So we ended up, I think, maybe 2 years ago in investigating into offloading the user plane of a BNG to ASICs. Oh, exactly, this is what's described here. So when you want to do this, you need to first of all look, what is a BNG? What are the main components? This is a slide that was discussed in the ZIBA project in the Open Networking Foundation. Slides are available there. First of all, what we said is, let's split the control and user plane. Even the 3GPP is doing that. So if the 3GPP is doing it, then probably there had been many discussions. So the AAA policy, the session control, LI control, and the routing control plane is all control plane. And I'm really in favor of putting that on generic hardware. But the per subscriber packet processing, taking off the headers, calculating or finding programming the next hop, doing the access list, doing the filtering, doing the accounting, that's something that should, in my view, happen on special hardware that has been exactly built for that. And then we also have the forwarding and the VPN function. That's the second blue box here. Now, the next thing we did is, OK, we have a programmable switching fabric that runs a routing stack. We use a slightly different system, but you can also use ONOS for that, because ONOS can do the trellis framework, can do the routing to the IP core network. So we said, that, OK, somebody in the fabric is going to handle that for me. Let's focus on the subscriber termination. So we took the right-hand side off, and we ended up in all the session-related stuff. And here's an example packet flow that everybody has in the network. Every operator has all these functions: classification, policing, PPPoE, NCAP, DCAP, access lists, accounting, lawful intercept. And most likely you put some MPLS headers on it, because I don't know who limited the VLAN range to 4096, but if I ever meet the guy, I'm going to ask him, but probably somebody in the room who did that? Fun? You did it? Yeah, but there's no Mr. IEEE, right? Anyway, so this is what we did. We analyzed all that. And let's say, I think it was roughly 2 years ago when this idea was pretty new. The first thing we did is, and I like that because I spent a couple of years in research, we went to the local university and I said, hey guys, you have become SDN experts. Here's a switch. Here's a bare metal switch. Have a look at it. First of all, let me know if this all makes sense. Like, can we really run Linux on it? Tick, yes. Now, are we able to program a BNG data path on merchant silicon? Back then, we used the available Broadcom chips, and it was, in principle, possible. We figured out we didn't have all the features, but we knew where the gaps were. Actually, there's also a scientific publication on that. But the feedback from that was, yes, there's no reason why this shouldn't work. And in parallel, there were new chipsets coming around, programmable chipsets that allowed you to program the data path and to enable all these functions. So time solved a part of this problem. So with the pioneering work from the Darmstadt University, we asked a couple of partners, do you want to do this together with us? Now, there were 3 different types of replies. Number 1 was, this doesn't work because it doesn't work. OK. Number 2 is, I know this works, but I'm not going to help you. OK. Number 3 was, this is cool, let's do this together. And the one who said that became our partner in that. And this was a company called RT-Brick, a smaller startup. But in DT, we have also invested in this company already. So RT-Brick took the pioneering work from TU Darmstadt, our knowledge, and we went off with 2 chipset vendors, and we built this thing. Here's the result from our work in one of our demonstrations. Here's a snippet of the P4 code, and okay, the font size is small, but if you would stand next to me, you would be able to read that. So this is plain P4 code, and everybody can read this. I'm not saying programming P4 in a way that the data plane and the resources on the chipsets is easy, but to get a start and look at and try something quick, this is easy, right? So there's not only P4 on the planet, there's also other languages. This is an example, and we could very rapidly do a prototype with this. This prototype code is available on GitHub, and we have also contributed this to the Open Networking Foundation, and whoever is interested in having a look, or maybe expanding it, testing it, giving feedback to us is highly invited to contact me here on site, or contact us via email, or however you like, right? So, and this is a screenshot from the speed test. So we have built a full prototype with an bare metal OLT with bare metal switches that are programmed with this code. And we have done that in the lab, and we have also brought that to a limited field trial. Right now, we have a programmable service edge or a programmed service edge on 2 types of silicon, on the P4 programmable, but also on another type of silicon. And there's another screenshot. Actually, you see these DevOps caps here. That was Robert's idea. Actually, the full picture has a picture of Georg, who's our operations guy, or one of our operations guy, and he's smiling. But due to privacy reasons, I took that off. But I want to highlight that all this development we have done together from day one, together with the operations team, and that's also key. Because if they like it, they later on need to operate it. And anyway, we are changing to become a DevOps organization. So what are the challenges? The rapid prototyping is not that difficult because you just define the PPPoE header. You make sure that during the discovery phase, the packets get directly punted to the CPU. You Google a bit. Some people have open source, some control plane stuff. It's not that difficult to do a rapid prototype. But once you want to do a real BNG, you have a couple of things you need to implement. And here's the list of it. And first of all, you need to tunnel these IEEE VLANs, right? Because if you look at a carrier network, there will always be the VLAN combination. Every carrier uses them in a slightly different way. Then we have the session termination issue, PPP over Ethernet. PPP over Ethernet in P4 is easy. PPP over Ethernet is also available on Broadcom chipsets, so that's not a hurdle anymore. You need to make sure that OAM runs. That's a tricky thing because of the keep alive, so that involves the CPU and the host path. Tunnel switching is something we're currently developing, and we are close to having that for L2TP. At least in Europe, that is common. I think also in the US that is used. Access list per subscriber. Once you define your data path, you need to make sure that you have well thought through how you apply the access lists, because they consume a lot of space on most likely the TCAM. So you need to really deep dive into the chip architecture. Accounting, very similar. Lawful intercept is something that's unavoidable, so you need to have a plan for that. HQS is a really complex thing, because hierarchical QoS is something you need if you have systems that are sort of at least theoretically overbooked. So if you have GPON, for instance, there's a couple of subscribers who share a 2.5 gigabit link, so you need to make sure that you shape the traffic so that no packets are dropped further down the road. Main reason for that is once you have done the accounting, you shouldn't drop the packets you've done the accounting for, right? So per hop QoS, I love per hop QoS, but it's difficult because of the requirements that we have from the legal side. Right, Michel, this is also your problem, right? You're not shaking your head. Okay, this is, everybody has this. Now, multicast, there are really different ways of implementing multicast. We do multicast inside the PPP session. That has a couple of benefits. I know that also some operators do the multicast further down the road, but then you have the problem with the QoS and the accounting again. But anyway, this is like the shopping list, and you need MPLS labels for the uplink. This is like the bare minimum I think that everybody needs, and we have implemented this on 2 types of chipsets already. Now, another thing is, how do I deploy the functionality, how do I spread it across the fabric? And that's also not straightforward. That depends on your business model, where you want to terminate the sessions, whether you have VNFs or whether you want to do everything in merchant silicon, whether you want to include the OLT into the process of packet shaping and NCAP, DCAP. There's no one size fits all, but there's a big enough playground for operators now to use this technology and mix and match and find your own way. As I said, shapers, so the QoS and the accounting are really closely related. So let's not oversimplify here. Dual chip versus single chip, it depends on which chipset you have, whether you have the required QoS functions on board or whether you need a separate chipset. You can also talk about programmable network cards there. Again, dependent on what is your use case. So yeah, this is basically the distributed approach. And here's a picture. So the way we do it at the moment is you have the OLT and we put the service edge on the top of the rack switch and we're done. This is just hosting control plane if we want to separate that. Okay, so much about the theory, but this is important to know that it's not that easy, but we have made good progress on this. Here's a schematic view on how it works in our P4 implementation. So you have Ethernet frames coming in. First of all, you check whether it's up or downstream packets, and here you see the headers that we use. So incoming from the core, we have one MPLS label and then the usual headers. And incoming from the access side, we have the stacked VLANs. We put an MPLS label on top because of the IEEE limit. Yeah, and so on. And here's a schematic view on how our P4-based prototype that we have contributed, how that works. Again, this also shows, this is a slide from Leo Nobach. If you want to have the details about that, contact Leo. I'm happy to connect you to him. So first of all, you check whether it's downstream or upstream. Take a look at the right-hand side. If it's downstream packets, you, at a certain point in time, need to apply the PPPoE header, swap the labels, and then do the QoS. In the P4 example, we have used metering, but that's not enough for a carrier case. And upstream side, it's included in the slide. I think they will be shared anyway. Yeah, here's the link again. It's on GitHub. There's 2 implementations available on GitHub. Number one is the easy one, which is the generic one where there's just the pipeline. That's something you can probably, after a training on the programming language, you can do on your own after 2 days. The tricky thing is once you want to map that to something like switch.p4, where you already have switching functionality in there, and you also need that functionality on the leaf switch. So merging it to something that exists already. We have 2 examples uploaded. We have not uploaded the control plane because we only have a stub control plane for the prototype, and the control plane in our case had been done by a partner who's not open sourcing this part. So the question is, and I hope that also in ONF this gets picked up if there's enough sufficient interest. The control plane is, for the prototype, is not that difficult. For a product, it's a different league, I would say. But that is something we think should be done in ONF, probably best programmed in the Golang. So I'm putting this on the table. Have a look at it and let us know if you want to join this activity. I don't want to be DT alone doing this. That doesn't make sense. Then we can just walk off and continue to do it on our own. But I think this is something the community should drive. And I'm also in contact with the chipset vendors, and there's big support also in supporting programmability, and I'm really happy with that. All right, so back to the big picture. I don't know how I'm doing time-wise. Oh, okay. Those who attended this morning, we've seen this already. This is the big picture. So in our distributed locations, we have the mobile traffic and the fixed line traffic arriving, and they are separate networks. And there are some good use cases for having separate networks, because if one network fails, you still can use the other one. So convergence needs to be well thought through. But we are able to couple fixed and mobile access already here, so we can offload, for instance, fixed line traffic to the mobile network. There is a use case for that. One is redundancy, the other one is increased bandwidth. You can use LTE for that. But the real cool thing is step number 2, where we say, okay, now we have programmable silicon here, and we know how to program the data path for fixed, and we also know how to program the data path for mobile. So let's use the same silicon. Let's use the same top-of-the-rack switch to program the data path here. And if you go to the demos over there, there's the MCORD demo from August and team, and there you can see an example how you can do a packet data gateway. In the long run, ideally, the control plane should converge, but that is 5G. People are working on that, and this time it's really happening. So I've been working on FMC and standardization for quite a while, since 2009. This time it's really happening. All right, now on the silicon side, what we envision is that if you look at the left-hand side picture, you have the forwarding plane, and yeah, I made this joke last time already in LA. There's D1, D2, D3, D4, so it's not only D1, D2 for the AT&T friends. No, the thing is, those are different types of forwarding devices. That can be network cards, that can be ASICs, that can be NPUs, that can also be plain x86. If we have an intermediate layer and we can plug in a driver, and at a certain level in this, at a certain level they speak the same language, we are independent on what is below, and this is what, for instance, Stratum is addressing, and I'm really happy seeing the progress in Stratum here. So Stratum might be a solution for this problem. We will look deeper into Stratum. So then the control plane, the BNG or mobile control plane, stays the same, and we can swap out the silicon. This is not to annoy our chipset vendors, but this is to keep competition there. And if you work for a company like Deutsche Telekom with 260,000 employees, you don't build a system that only depends on one vendor. So we always go for dual vendor, just to be not dependent. Yeah, I think UPAN Stratum is going into that direction. That looks good to me. So here's a summary. The service edge at Deutsche Telekom is running. It's running in a field trial. We've done lab testing. We can scale up to 15, 20,000 subscribers already on the pipeline, and we haven't optimized it yet. So this looks good. We have a limited field trial, so I think we're the first who have a programmable service edge out in the field. It's friendly customers, very friendly customers, but they enjoy accessing gigabit internet from Deutsche Telekom over a BRAS BNG that's implemented with merchant silicon. Currently, we are developing a product-grade solution along these lines. Stay tuned for further news on that. The API thing, we want to share our experience with regards to how an API should look like. Initially, actually, I wanted to have that ready in October. Yeah, now it's December. We think about Christmas. It will take a few more weeks, but I'm happy to share our first view on how the APIs should look like, and hopefully also harmonize with the UPAN work in ONF. We have fully decoupled hardware from software. And as I said, we want to just have competition on silicon level. We want the best solutions here. In the community, the P4 code is there. Bear in mind, it doesn't come with a control plane. We're currently thinking about how to maybe add a simplified control plane so that you can walk off and experiment with it. The deployment option that I was talking about, there's a lengthy presentation available at the ONF. We're in discussion within CBA. Yeah, the architecture work is happening in Ziba. The actual implementation, in my view, should happen in UPAN. And yeah, the APIs. So I talked a lot about this, and one idea we have is that in the ONF we should have a reference implementation integrated into the Ziba exemplars, where we can terminate subscriber sessions with PPP or even IP over Ethernet with access lists with all the QoS stuff. That would be great, because that would also push further in the industry for disaggregation. With that, I would like to close, and I don't know if there's still time. If somebody has a question, feel free to ask.
Hans-Jürgen. So we do have time for 1 or 2 questions.
Hello. My question is regarding
about that when you think about these kind of solutions to deploy in the network, that is necessary to have maybe an NFV strategy or SDN strategy before to think on that. In terms, for example, some service provider which are not higher in market, and what happened with that? I mean, if we, for example, in our case, if we need to define first our NFV strategy for the whole network before to start with that, or maybe we will run in parallel.
We're running a big virtualization program in Deutsche Telekom, and at the beginning of that program, I was part of that. This happens on the access side. So internally, we have decoupled what is happening on the access side with what's running in the big data center programs. We are using their findings, and they are using our findings, but I don't want to be dependent on something that's happening really further down in the network. So the control plane, everything is happening inside the POD. We call that the Las Vegas principle. What happens in Vegas stays in Vegas. So you enter through one API, and the POD magically does something. For instance, the virtual wiring of the subscriber sessions. Nobody outside the POD needs to know whether the flow goes over leaf switch 1 or 2. It's just irrelevant. The only time when you need it is when you want to debug it. But I have seen too many designs in network where internals, really technical internals from remote systems had been incorporated in centralized systems. So whenever you change something, you add a knob or you change something, you have to change your IT. And this is what adds the delay in rolling out new services. So the short answer is, in our case, it's decoupled from the overall virtualization strategy. I don't need to have a virtualization guru telling me what to do here. I think we know, right? But we use the synergies. I don't know if that answered sort of your question.
So next question. So you have the access, the SE, right? Gonna have a lot of traffic, especially 5G coming. So you got a lot of network slicing services. How are you gonna maintain the QoS end-to-end and SLA to be able to stand up multiple slices?
Multiple sites. So what you really need to cater for is manage QoS where you need it, so where the possible bottlenecks are. So further up from the POD, the network is congestion-free. So take here, that's done by capacity planning. So by applying such a policy, you can already reduce the amount of stages for H-cores you have. The idea here is that the top of the rack switch, or you could also use the OLT, but currently I think it's the top of the rack switch. That's the central gateway for the downstream QoS. So whenever traffic comes in from mobile or fixed, they go through the same silicon, and there the QoS policies get applied. And this point in the network knows the available bandwidth. That's the current idea. And I think that's going to work. But the fancy service creation, so for instance, imagine you have an enterprise customer that comes with a printout of the access list, like 50 pages of access list. You don't put that on the top of the rack switch. If somebody pays for such an access list, we'll buy a server and apply the access lists on a VNF.
I don't have a question. I just want to add one suggestion, re-emphasize what you just mentioned for using Stratum. It seems like the use case here fits the Stratum use case a lot. Once because using one P4 program to be able to handle multiple merchant silicons, even if it's a fixed pipeline, is something that Stratum is going to support. And the other thing is that right now there are some cases that P4 cannot support, but you guys need it, including QoS, like very tight control over the QoS. And that's, again, another thing that Stratum is going to provide using hopefully the GNMI. So I strongly suggest that what you just mentioned will do it.
Yeah.
Because
sometimes it's also a matter of available time, but I figured
yeah.
out I need to do more in the UPAN group. Okay.
Thank you.
Thank you.